Hello everyone, I'm Sharon and I'm going to talk about crystal, its defects and few topics related to it. So what is a crystal? A crystal or a crystalline solid is a solid material whose constituents are arranged in a highly ordered microscope structure, forming a crystal lattice that extends in all directions. So crystals are rarely perfect. They contain large number of defects or imperfections, which influences the behavior of the material. So because of these defects, the actual strength of the metal is less than the theoretical strength. We have four types of crystal defects, that is point defect, line defect, surface defect, and volume defect. Coming to the point defect, it is nothing but the irregularities or the deviations of atoms from their ideal arrangement in a crystalline structure. This is caused due to plastic deformation. Under this, we have four types, that is vacancy point defect, interstitial point defect, impurity point defect, and interstitial impurity point defect. So first, let's talk about vacancy point defect. Vacancies are nothing but missing of atom from its original structure. This arises due to thermal shocks during crystallization or plastic or mechanical deformation. As you can see here below, a perfect crystal diagram and the vacancy point defect where the missing of the atom from its original structure takes place. Coming to the interstitial point defect, it is nothing but the extra atoms positioned between the atomic sites. It is caused due to plastic deformation. As you can see the diagram here, we have the interstitial atom which is positioned between the atomic site. In interstitial point defect, the atom will be of same kind or different kind and occupies between the regular atomic structure. Coming to the interstitial impurity. When an impurity atom is small in size, space between the regular atomic structure, as you can see to the right. Coming to the substitutional impurity. Substitutional defects. When an impurity atom replaces or substitutes its parent atom. For example, brass here experiences substitutional defect, where zinc is a substitution atom in a copper structure. Coming to the Frenkel defect. It is nothing but ion is displaced from a regular structure to an interstitial site as the interstitial space is small. Figure B describes the Frenkel defect. Coming to the Schottky defect. It is a pair of positive and negative ion which is missing from its original structure so that neutral charge is maintained in the crystal. As you can see, figure A, it describes the Schottky defect. Now coming to the line defects. It is a defect arising out of missing out of a line of row of atoms from its designated ordered arrangement. This is caused due to thermal stresses during plastic deformation. So here we have edge and screw dislocations. According to the diagram below, an edge dislocation occurs when an extra atom is inserted into one plane of the crystal lattice. Under the edge dislocation, we have positive edge dislocation and negative edge dislocation. In positive edge dislocation, it is nothing but if the vertical plane starts from the top of the crystal and never reaches to the bottom, while it is the opposite in the negative edge dislocation, where if the vertical plane starts from the bottom of the crystal and never reaches to the top. Screw dislocation is nothing but here atoms are displaced in two separate planes, perpendicular to each other, or defects forming a spiral around the dislocation line. Screw dislocation marks the boundary between the slipped and unslipped parts of the crystal that can be produced by cutting the crystal pathway and then shearing down. You can see the diagram below, which shows the screw dislocation. Coming beneath that, the defect can be imagined by cutting of crystal structure partly by a knife and shearing of a part of crystal along the plane parallel to it. So the arrow in the clockwise direction shows the upper portion of crystal shifted towards right with respect to lower portion, and the arrow in the anti-clockwise direction shows the upper portion of the crystal shifted towards left with respect to the lower portion. So diagram to the left shows the screw dislocation line and the zone of shear when the crystal structure is cut. Coming to the surface defects or plane defects. Surface defects are associated with boundaries that are separate regions of the materials and have different crystal structure. It is a two-dimensional defect. It is caused due to change in orientation of the atomic planes and stacking sequence of atomic planes. It is caused during solidification or mechanical or thermal treatment of material. It affects the mechanical properties, electrical resistance, and corrosion resistance. Stacking fault. It is surface imperfection caused by stacking of one atomic structure. So the figures A, B, C, D show what stacking fault is. Coming to volume defects. Volume defects are associated with three-dimensional atomic structure. As I've told you before, surface defects are associated with two-dimensional, whereas volume defects are associated with three-dimensional atomic structure. So these defects occur during solidification of materials. It is caused due to the presence of foreign particles, inclusions, and large voids. As we see the figure below, volume defects in crystals are three-dimensional aggregates of atoms or vacancies. They manifest themselves macroscopically as pores and cracks. So let us know what is plastic deformation. When a material is deformed beyond the elastic limit, plastic or permanent deformation occurs, where the material does not regain its original size and shape. The ability of a material to undergo permanent deformation is very important in all engineering applications. So let us have an overview of the stress-strain curve, where these terms are related. That is limit of proportionality, elastic limit, yield point, ultimate tensile strength, and fracture. So plastic deformation occurs by slip, twinning, or by both. So let us know what is slip. A slip is a line defect. A slip or plastic shear is a deformation mechanism in which one part of the crystal moves or glides or slips over another part along certain planes at same distance direction called as slip planes. The atoms move through interatomic distances relative to their original position. So the plane at which slip takes place is called as slip plane, and the direction at which it occurs is called as slip direction. The figure to the left shows a single crystal structure of the slip, where the terms slip direction, slip step, slip plane is shown. So the combination of slip plane and slip direction is called slip systems. A series of slip planes sliding on one another appear like a band. So stage 1, 2, 3, 4 shows the slip in a single crystal. Coming to twinning. Twinning is a plane defect. Atoms will move at different distances and in different directions, in different planes. After twinning, the direction of lattice will change such that one half of the twin is the mirror image of the other half. Applied stress to a perfect crystal. So the figure A and B shows before twinning and after twinning. A may cause a displacement of the atoms. B causing the formation of a twin. Note that the crystal has deformed as a result of twinning. The plane across the two parts of the crystal form a mirror image called as twinning plane. So what are the causes for twinning? It occurs by plastic deformation, that is hot or cold working, called as mechanical twins. By thermal treatment or heat treatment, called as anneal twins. Twinning by shock loads are called as Newman twins or Newman bonds. So far I've spoke about crystal, its defects, and the topics related to it. Thank you.